so first thing we're going to talk about is the peripheral receptors. So we're going to start out over here talking about sensory receptors. So you have three main categories of sensory receptors with little breakdowns between each one. So first off, we're going to look at thermoreceptors, which are big on temperature. They can sense cool, cold, warm, and hot. But if you get super hot or super cold, then that actually goes down to our nociceptors, which have to do with pain. And there are four subtypes of nociceptors. There's mechanical, so that's like your sharp objects. There's thermal, so that's extreme hot and extreme cold, like I said earlier. There's chemical, and that's things like serotonin or histamine or bradykinin. And then there's polymodal, which is basically a combination of all of these. So if you had a polymodal nociceptor, you would have mechanical, thermal, and chemical nociceptor all going on at the same time. Flare is the redness, and edema is the swelling that you get with injuries. So these also happen due to nociceptors. And then you also have your level 2, which is your partial thickness burn, or your level 3, which is your full burn. So the difference between level 2 and level 3 is level 2 is actually really painful because you haven't burnt down past that free nerve ending. Whereas level 3, you've burnt all the way past that free nerve ending, so it's no longer painful anymore. Mechanoreceptors have to do with your touch, think mechanical touch, and there's 5 subgroups of that. So you have your hair follicles, which are basically your free nerve endings that are wrapped around the hair follicle, so if you move the free nerve ending, you know that you've been touched, and you can actually sense it up to a single hair follicle, which is pretty cool. Then you have your Meissner corpuscles, and those have to do with pressure, specifically in your fingertips. You have a lot of them in that. You have your Merkels, which has to do with indentation, so they tend to be bigger and disc shaped, and so you can feel like an indentation on the skin. You have your Pacinian corpuscles, which are also bigger, and they sense vibration. And then you have your Ruffini's corpuscles, which have to do with proprioception. So there's different kinds of proprioception. There's limb position sense, which has to do with stationary, like if I'm just sitting here, I know my arm's right here and my other arm's right here. Or there's also kinesthesia, which has to do with moving in space. So like if I'm running, I know my arms are moving on either side of me. There's 3 specific types of proprioceptors. There's mechanical receptors, which are also called joint receptors, and those are obviously inside of your joints. There's muscle spindles receptors and GTOs, which are inside of your muscles. And then there's mechanoreceptors, which are these 5 receptors up here. Now we're going to move on to different parts of a receptor. So we know that receptors are specific and they actually have adequate stimulus. So for every receptor, there are certain things that make them be stimulated. Like we know for our thermoreceptors, it's temperature. Nociceptors, it's different kinds of pain. And mechanoreceptors, it's touch. So they are adequate stimulus. They need those stimulus to be specific. We also know that sensory pathways are modality specific. Basically what that means is that when we have a sensation, we don't just go, oh, we have a sensation. We know that the CNS interprets that sensation to be either pain or temperature or touch or something else, so they're modality specific. We also have stimulus transduction. So when a stimulus actually comes in, it's usually a physical stimulus, like I poked you with a sharp object. But we take it and turn it into an electrical signal, which is also called a receptor potential, that the CNS can then interpret. We also have different stimulus intensity, and that's based off of the size of the stimulus and the duration of the stimulus. Usually you have to get to a generator potential, which is basically that threshold that you have to hit to get an action potential. So if I don't have the size and duration of the threshold to get to my generator potential, I won't have an action potential. And then you have receptor fields, which are those areas innervated by a single afferent neuron or a single sensory neuron. Different areas on your body have different receptor densities, which is the numbers of receptors per the given area in your body. So something that is an example of a receptive field is a 2-point discrimination. So the location for 2-point discrimination can be variable. Basically, like your hands, you have a very small 2-point discrimination, which basically means I can put something like super duper close together and touch it, and I can still feel that there's 2 different things touching me. Versus in your back, you can't. You put 2 things super close together in your back and you can't feel it. You think it's just one thing. Going on to receptor adaptations. So usually with the receptors, you have a decrease in generator potential with a sustained stimulus. Basically, like if I put on a really itchy sweater, at first I'm going to feel it a lot, but then since I have a sustained stimulus, my generator potential or my threshold goes down and I no longer feel that it's itchy anymore. Certain receptors are rapidly adapting and others are slowly adapting. Rapidly adapting receptors are ones that you feel at the onset of the stimulus and the end of the stimulus. You don't really feel them in between. So examples of that are motion and also vibration. So you'll feel it when it starts vibrating, and you won't feel it as it keeps vibrating, and then you'll feel it when it ends vibrating. Slowly adapting receptors are ones that are continuous, but they decrease in amplitude. So like if I'm continuously giving you like a pressure or form, you can still feel that the whole time, but you just become a little less aware of it. An example of that is stereognosis. And then axonal classifications, we classify axons based off of their diameter and based off of their conduction velocity. Before we get into that though, we'll talk about how peripheral nerves are actually surrounded by 3 layers of the connective tissue, which are an extension of the meninges. So you have your epineurium, which is an extension of your dura. And then inside of that, you have your perineurium, which is an extension of your arachnoid. And then inside of that, you have your endoneurium, which is an extension of your pia. And this one is super important because your endoneurium actually guides regrowing axons. So if you have like a peripheral nervous system injury, then your epineurium is what's going to re-guide those regrowing axons as they're going back. There's 2 ways to classify axonal classifications. Like I said, there's the ABC classification, which is your diameter. When you think about it like that, think that A is greater than C. So A is faster than C. Bigger diameter, faster. That's your muscle cells or muscle fibers. And then you also have your 1 to 4, that's Roman numerals classification, and that's your conduction velocity, thinking that your 1 is faster than your 4. So in total, bigger diameter and faster conduction velocity would be like your IA, and those are much faster than your lower diameter and your smaller, which would be like your IC. And that's peripheral receptors.